Hello, welcome to Lecture 9 of Electrical Circuits 1. Last time we talked about nodal analysis. We did a number of examples and then we introduced mesh analysis. At the beginning of this lecture I want to do a quick review of the steps to do a mesh analysis of a circuit. Now last time we set up the mesh analysis approach, but my example circuit did not contain any current sources. Current sources will create constrained loops. I'm going to talk quite a bit about constrained loops today and do examples of that. Following that, we'll just do some additional generic mesh analysis examples. If you want to do some reading, the related educational modules are in section 1.6.2. Okay, a review of the steps associated with mesh analysis. And remember that I've digested these a little bit and condensed them from the approach that I gave you for nodal analysis. Each step in nodal analysis has a corresponding step in mesh analysis. What I've done is combine different steps, so I came up with fewer total steps. First step, choose the mesh loops and identify your mesh currents. The approach towards doing this that I recommend, okay, you can do whatever you want to as long as you don't violate KVL and KCL and Ohm's law, is that you kill your sources first. Then you can identify any enclosed but non-overlapping areas in the circuit. It'll become more clear what I mean by that as I do more examples. Finally, I follow the circuit elements that bound these closed areas. Those form my mesh loops. My mesh currents flow around those mesh loops. Now I want to emphasize that the mesh currents are not necessarily a physical current that exists in the circuit. They are a mathematical parameter. They are a set of information from which you can find anything else. If you need to find the current through a particular element, you need to sum up all of the mesh currents that go through that element. After you've identified your mesh loops, put your sources back in and identify any constrained loops. I'm going to hit this one pretty hard at the beginning of the lecture today. After we have identified our constrained loops, we can apply KVL around all of our mesh loops. And we will use Ohm's law to write KVL in terms of these mesh currents. Now this approach will give us n equations in n unknowns, where n are the number of mesh loops in the circuit. When I solve those equations, I can determine the mesh currents. The mesh currents, as I said before, are not necessarily a physical current in the system. You can use those, however, to find anything else that you need to know about the circuit. So use your mesh currents to determine any actual desired parameters that you want. Okay, in the last lecture I mentioned constrained loops. I said the words about how to create them and what they're useful for. However, I didn't do an example of a circuit with a constrained loop in it. So in this lecture, I want to reiterate the words about how constrained loops are created and then do some examples that illustrate the point. So, constrained loops typically pass through your current sources. Current sources give you a known current in the circuit. Okay? In general, that provides you some direct information in a mesh analysis. These constrained loops allow you to incorporate that information directly without writing a separate equation. Okay? Now, the choice of your constrained loops is somewhat arbitrary. There isn't necessarily one unique choice of constrained loops that is correct and anything else is wrong. Okay? There are usually a variety of different constrained loops you can choose, any one of which will work as long as you use it correctly. So know why they're there and know how they're created rather than just trying to pick something that you think is right. Okay? In general, each current source has a constrained loop going through it. And in fact, each current source should have one and only one constrained loop going through it. Now, that's not a solid requirement, but that's a typical way to approach this to make your life easy. When you create a constrained loop, each of those will pass through a current source. The direction and magnitude of the constrained loop must be consistent with the direction and magnitude of the current going through the current source. Okay, those have to agree. Okay, now let's do an example of a mesh analysis for a circuit that contains current sources and will thus be analyzed using constrained loops. I want to use mesh analysis to determine the current I4. That's the current through this 4 ohm resistor. My assumed direction is positive left to right. So the first thing I want to do here is identify my mesh loops. To do that, I'll kill my sources. That means I open circuit current sources and I short circuit voltage sources. So this circuit, the 2 amp current source, becomes an open circuit. The resistors here do not change. This 10 volt voltage source becomes a short circuit. This resistor doesn't change. This 1 amp current source becomes an open circuit. And this 8 volt voltage source becomes a short circuit. Now I look for enclosed non-overlapping areas in the circuit. I have only one. It's right there. This one isn't enclosed because there's a gap. These two are not enclosed individually because there's a gap between them. So my only mesh current goes around this set of circuit elements here. I'm going to call that I1. Now I'm going to do KVL around this loop. I'll get only one equation in one unknown. Now I'm going to identify constrained loops for this circuit. I have 2 current sources, therefore I'm going to anticipate coming up with 2 constrained loops. They're arbitrary, but they do have to pass through the current sources, so I need a constrained loop that passes through this 2 amp source. Its magnitude and direction has to agree with this 2 amps. So I'm going to just arbitrarily pick this as going around this upper loop. Okay, if the current's going clockwise, it's going in the correct direction here. I'm going to label its amplitude. It has to be 2 amps. Now I need another constrained loop for this current source. It needs to be going downwards through this leg, and it needs to have a magnitude of 1 amp. I'm going to arbitrarily claim that that's my constrained loop here. So here it's going down, and it has an amplitude of 1 amp. Now, I'm going to do KVL around my one mesh loop. I need to account for all the currents that go through any particular circuit element. For example, this 2 ohm resistor has current I1 going through it. It also has a 1 amp constrained current going through it from left to right. And it also has this 2 amp constrained current going through from right to left. Now remember, when we set up our voltage polarities for each element, I need to set those polarities relative to the direction of the mesh current that I'm dealing with. So I need to assume that my positive polarity is on the left relative to the right for this 2 ohm source. This current is going to enter the positive voltage node. So if I do KVL, and let me just start down here at this lower left-hand corner, going clockwise through here, I hit this negative terminal first. This becomes a negative 8 volt contribution. Now I'm going to get the voltage across this 2 ohm resistor. Voltage is resistance times current. So I have a 2 ohm resistance times the total current through this resistor. Well, I1 is, of course, entering the positive voltage node, so it causes a positive contribution. The 1 amp current source is going to be entering the positive voltage node. It will be considered to be positive. The 2 amp constrained current is entering the negative voltage node of this resistor. It disagrees with the passive sign convention. It is a negative contribution. Now we can move on to this 4 ohm resistor. Its voltage drop with the appropriate polarity relative to I1 is the resistance, 4 ohms, times the current passing through the resistor. I have I1 going left to right, and through this one I also have the 2 amp constrained current going from right to left. It will be negative. And that is plus. Now I have this 10 volt source. As I'm going clockwise, I see the positive terminal first. So I have a plus 10 volts. And finally, this 6 ohm resistor, its voltage drop, with its polarity being positive where the mesh current enters the circuit element, is its resistance, 6 ohms, times the total current passing through this element. The only current going through this element is I1. None of these constrained loops pass through the 6 ohm resistor. So now I have one equation and one unknown, which I can solve for I1. I'll go ahead and move to the next slide in order to do that. Now if I solve that previous equation for my mesh current, and let me relabel my mesh current I1, my constrained current 2 amps, and my other constrained current 1 amp. When I wrote my equation, I can solve that for I1. It turns out that if I solve that, I1 is 0.667 amps. So it's 2/3 of an amp. It's positive. It's in the direction shown. Now, my original problem statement, I didn't want I1, I wanted the current through this 4 ohm resistor, I4. In order to get any physical current in the circuit, I need to sum all of the contributing mesh currents that go through that element. So through this element here, I have I1, which is positive relative to my defined direction for I4. I also have a 2 amp constrained current going this direction, which is in the opposite direction to my defined direction for I4. So I4, if I sum the mesh currents that go through that, that is I1 minus 2 amps. So I4 is actually minus 1.33 amps. So it is actually a positive current going in the other direction. Okay, keep in mind that once you've found the mesh currents, you have generally not finished the problem. You still need to use those mesh currents to find any physical parameter in the system. They don't correspond to anything directly in the circuit. Now, I mentioned earlier that the choice of your constrained loops is typically not unique. You have a certain amount of ability to define them yourselves as long as they agree with your actual current sources. Now, your mesh currents, okay, the mesh current I1 is unique, okay? There's really only one mesh current in this circuit. However, if I look at this 2 amp current source and create a constrained current for this, all I need for that is that it's going from left to right up here and has an amplitude of 2 amps. Let's make this constrained current go all the way around this loop. So this is a constrained current. It is 2 amps. Okay, it comes back to where it started, and it agrees with the magnitude and direction of the current source that it goes through. Let me keep this one the same. Okay, so I have the same choice for this one as before. Now if I do KVL, I'm going to start at the lower left-hand corner again. I have a negative 8 volts. Coming into this 2 ohm resistor, its voltage polarity is still has to agree with the direction of current I1. So I have plus 2 ohms times I1 is a positive contribution, plus 1 amp is also a positive contribution. Okay. Now going through this 4 ohm resistor, the voltage is the resistance times the total current passing through this. Now the only current going through this resistor is the current I1. Neither of my constrained currents pass through this resistor, right? Hitting this voltage source, I see the positive terminal first, plus 10 volts, and then this 6 ohm resistance times its total current. I have I1 going through that resistor. And now I have this 2 amp constrained current also going through this resistor. It is going in the same direction as I1, so it is entering the assumed positive voltage node, so I have a plus 2 amps. Then I'm back to my starting point. This sums up to 0. Now if I solve this, I end up with I1 is minus 1.33 amps. Okay. This is still a mesh current. In order to find the current that I want, I4, I need to use my mesh currents, sum up all the currents passing through that resistor to get this one. However, now in the 4 ohm resistor, the only mesh current passing through that is just I1. As I said before, none of the constrained currents go through that. So in this particular case, I4 is equal to I1, which is minus 1.33 amps. My mesh current number was not the same value as the mesh current for the previous choice of constrained loops. However, my final physical current between the two choices of constrained loops is the same. Okay, because you've no longer put any constrained currents through this resistor. Just for kicks, let's do yet another choice of constrained loops. Okay? My mesh current is still going to go through the same elements that it's always done. Okay? If I kill the sources and look at enclosed non-overlapping areas, I still only get this one. That uniquely defines this mesh current. Now, I need to choose constrained currents. Let's stick with the same choice as the last one that I did for no particular reason. So I have 2 amps. It's going to go all the way around the outer perimeter of this circuit. Now, for this constrained loop, let's choose it over here. If I make this 1 amp going counterclockwise here, it agrees with the magnitude and direction of the current through this current element. Now I'm going to do KVL around my single mesh loop. Just to be consistent, I'm going to start at the lower left-hand corner again. The first contribution I get is negative 8 volts. Now I get a 2 ohm resistance times the total current going through this resistor. Now I only have a single current. I1 is the only current that goes through the 2 ohm resistor. Okay. Next thing I encounter is my 4 ohm resistor. So I have 4 ohms times the total current going through that resistor. I have I1 going through that. Remember, my voltage polarity is chosen relative to I1, so I1 is always going to be a positive contribution. And now this 1 amp constrained loop is actually going from right to left. It's entering the negative voltage node, so this 1 amp causes a negative contribution to this 4 ohm voltage drop. Here, I still encounter my positive voltage terminal of this 10 volt source first. Now going down, my final element is this 6 ohm resistor. Its voltage polarity is plus minus relative to I1. So its voltage drop is plus 6 ohms times I1 is a positive contribution. I have a 2 amp constrained current going through this one. It is entering the positive voltage node, so I have a plus 2 amps. And then I have an additional constrained current, 1 amp, which is now going from left to right, which makes it enter the negative voltage terminal, so it is a minus 1 amp. That brings me back to my starting point, so that sums up to 0. Now, if I solve this equation for I1, I get minus 0.33 amps. Okay. Every single one of our choices of constrained loops have given us different values for this mesh current. However, this is not a physical current anywhere in the circuit. In order to find an actual physical current like I4, remember it is positive in this direction, I need to sum up all the individual contributions. So I4 is the same direction as I1, so it is I1, and it also has a negative contribution from this 1 amp constrained current because it is actually going right to left in this element. So it's I1 minus 1 amp. Minus 0.33 minus 1, I4 is minus 1.33 amps. So for any physical current in the circuit, I will get the same solution regardless of my choice of constrained loops. To do another example of a circuit which contains current sources and thus is more easily analyzed using constrained loops. Okay, for this particular circuit, we want to determine I10, the current through the 10 ohm resistor. It's assumed to be positive downwards. Okay, we don't know the actual final direction, we're assuming this. Okay, we need to determine our mesh loops and our mesh currents. We do that by killing the sources. This current source and this current source will become open circuits. This voltage source and this voltage source will become short circuits. So opening up the 2 amp source, there's a resistor there that I don't need to change, shorting the 120 volt voltage source. That resistor doesn't need to change. I short this 80 volt voltage source, and then I have a resistor on this top leg. This current source becomes an open circuit. So now this little area here is no longer enclosed. It's got a gap in it. Neither of these areas are enclosed because this current source creates a gap. My only enclosed area is this large outer one. So I'm going to choose my mesh current as going around the perimeter of that area. I only have one mesh current for this example. I'm going to call it I1. Now, since I have current sources, I need to choose my constrained loops. I think I'll just make a constrained loop in this upper left-hand corner here. Call that 2 amps. The only requirement is that the constrained loop passes through one and only one current source. Its magnitude and direction agree with the magnitude and direction of that current source. So this loop is going up on the left side of this area. Now I need to choose a constrained loop for this current source. I'm going to rather arbitrarily just say that it's going to be in this upper triangular area. It will be 4 amps, so its magnitude and direction agrees with this 4 amp current source. Now I'm going to do KVL around my one loop. I hit the negative terminal. If I start out down here, I hit the negative terminal of this voltage source first, so I have a minus 120 volt contribution from this. My voltage polarity is chosen relative to the mesh current I1, so this is my positive voltage node on this resistor. So I end up with a plus 10 ohms. Its voltage is the resistance times the total current going through it. I1 is going through this and entering the positive voltage node. It becomes a positive contribution. The 2 amp current source is entering the negative node of this resistor. It's going down on the right-hand side of this little area here. It's a negative contribution. Next thing we hit is this 20 ohm resistor. Its voltage is the resistance times the total current passing through it. I have I1 passing through it, and I also have this 4 amp constrained loop going through it. However, the 4 amp constrained current is going right to left up here, so it is actually a negative contribution. This 80 volt source has a negative terminal that I encounter first. It becomes a negative 80 volt contribution. Finally, I have the voltage across this 40 ohm resistor. So I have 40 ohms. The only current going through that is the mesh current I1. Now we're back to my starting point, so that all sums up to 0. I have one equation and one unknown that I can solve for I1. If I do that, I get I1 is approximately 4.29 amps. Remember that this is not actually a physical current anywhere in the circuit. To find this physical current, the actual current through this resistor, I have to sum up all of the mesh currents going through that resistor. So this current here has I1 and a 2 amp constrained current going through it. My assumed positive direction for I10 is opposite to I1, so I1 is actually a negative contribution to this. So I10 is equal to minus I1. This 2 amp current is going in the same direction as I10 through this resistor, so it becomes a positive contribution. So I10 is minus 4.29 plus 2 is minus 2.29 amps. So the current is actually going upwards in this leg here. Now let's take another look at this example. Back when we did nodal analysis and we were determining our constrained nodes, the constrained voltages, at one point we said it's not really a big deal if we don't pick our constrained nodes correctly. What we could do is make all of our nodes independent and then write constraint equations that caused explicitly the voltages at different nodes to be related. We can do the same thing with mesh analysis. So for this example, we don't need to choose really constrained loops. For example, here I can call this a mesh current, and I can say that that's I1, some unknown current. Now, this current is the only current that goes through this 2 amp source. Therefore, my constraint equation would be that I1 is equal to 2 amps. Right? The only current going through here is 2 amps. I1 has to be 2 amps. Now, if I do the constrained loop, I can see directly that this is 2 amps. I don't have to write that equation, but this equation doesn't bother me. I can leave this as an unknown and write this equation. Likewise, this is an enclosed non-overlapping area. I can create this as mesh current I2. This is also an enclosed non-overlapping area. I can choose this current as mesh current I3. Now I can write KVL around loops 2 and loop 3. So let's do loop 2. Starting at the lower left-hand corner rather arbitrarily, I have minus 120 volts plus 10 ohms times I2 minus I1 plus the voltage across this current source. I don't know what the voltage is across a current source. I have to define that as an unknown. So I'm going to say that this voltage difference is V sub x, and I'm assuming that its polarity is in this direction. So now I have a minus V sub x plus 40 ohms times the only mesh current going through the 40 ohm resistor is I2. That all sums to 0. I can also write KVL around loop 3. Just arbitrarily, I'll start up here. I have a 20 ohm resistance. The only mesh current going through that resistor is I3 minus an 80 volt source plus the voltage across the source, V sub x. All of that is 0 because I've come back to my starting point. Now I have unknowns I1, I2, and I3 and V sub x. I actually have 4 unknowns and only 3 equations. I have to write another equation. I know what the current has to be in this leg here. It has to be 4 amps and it's going in this direction. So I2 and I3 have to algebraically sum to give me this 4 amp current. Now I2 is going in the same direction as the 4 amp source, so it's a positive contribution. So I'm going to write what is called a constraint equation. So I2, now I3 is going in the opposite direction as the 4 amp source. It's a negative contribution. So I2 minus I3 is equal to 4 amps. We now have 4 equations and 4 unknowns. These can be solved to determine I1, I2, and I3. They will ultimately give me the same solution I got my previous way. I just have a more laborious approach towards getting there if I don't identify my constraint loops. Still, as long as I follow the rules, I'll be fine. Let's do another mesh analysis example. I want to use mesh analysis to determine the current I in this circuit. I first need to identify mesh loops and mesh currents. If I kill my sources, shorting these 2 voltage sources, I get an enclosed area here, an enclosed area here, and an enclosed area here. I have 3 mesh loops. I don't break the loops anywhere. I don't end up with any constrained loops because I have no current sources. I'm going to rather arbitrarily choose this loop as my mesh current I1, this as I2, and this as I3. Now I need to apply KVL around each of these loops. For loop 1, starting in this corner, if I follow it clockwise, the same direction as I1, I first hit this 4 ohm resistor. The only current going through that is I1, so its voltage drop is 4 ohms times I1. Next, I will hit this 3 ohm resistor. The total current going through that is I1 minus I3. Remember that your assumed voltage polarity is based on the direction of the mesh current that you're following at the moment. So I1 invokes a positive contribution. I3 is entering the negative terminal. It becomes a negative contribution. Likewise, for the 2 ohm resistor, I have 2 ohms times I1 minus I2. I'm back to my starting point. That all sums to 0. If I group terms, I have 4 and 3 is 7 plus 2 is 9 times I1 minus 2 times I2 minus 3 times I3 is equal to 0. Remember that you can check your results by looking at the multiplicative terms on each factor. The term multiplying I1 for your first loop should be the sum of the total resistances in the loop, 4 plus 3 plus 2. The multiplicative factor on I2 should be the negative of the resistance through which both of these mesh currents pass, negative 2. Likewise, I3 should become a negative 3. Let's do loop 2. Okay. If I start down here, I hit the negative terminal of this voltage source first. That's a minus 76 volts plus 2 ohms. Now my voltage polarity for the 2 ohm resistor is going to be based on the direction of I2. So I2 becomes positive for this equation minus I1, which is negative, plus the contribution for this one, which is a 5 ohms times the total current is I2 minus I3. Grouping terms, I have a 2 times I2 plus a 5 times I2 becomes a 7I2 minus 2I1 minus 5I3 is equal to 76. I'm going to move to the next slide to write my final equation. Okay, these are the directions of the mesh currents that I chose and their associated loops. I still need to write my equation for I3. So KVL around loop 3, if I start at this lower left-hand corner of this loop, I have 5 ohms following this current I3 clockwise. Now I3 becomes a positive contribution, and I2 is going the opposite direction through this 5 ohm resistor. I have a contribution from this 3 ohm resistance, which is its resistance times the total current. This is now the positive relative to the negative node because I3 is entering the positive node. So I have 3 ohms times I3, and I1 is going in the opposite direction. I then hit the positive terminal of this 72 volt voltage source, and I'm back to my starting point, so that sums to 0. So I end up with 5 plus 3 is 8 times I3 minus 5 times I2 minus 3 times I1 is equal to minus 72 volts. Again, the multiplicative factor on I3 is the sum of the resistances in that loop. The multiplicative factor on I2 is the negative of the resistance connecting these two loops. The multiplicative factor on I1 is the negative of the resistance between these two loops. That pattern only holds if you choose all of these to be in the same direction. They all have to be clockwise. Otherwise, you're not wrong, you just don't get this pattern. So I have 3 equations and 3 unknowns, I1, I2, and I3. If I solve those, I get I1 is equal to 1 amp, I2 is 9 amps, and I3 is minus 3 amps. So I've got my mesh currents, but I'm not done. None of those are actual physical currents in this circuit. In order to find the physical current I need to sum all the mesh currents in that element. So I is I2, which is going in the same direction as I, minus I3, which is going in the opposite direction. So this is 9 minus a minus 3 amps is equal to 12 amps. And it is positive downwards. One last example on mesh analysis. Okay? We're going to determine the current I10 through this 10 ohm resistor using mesh analysis. Okay? First thing I need to do is identify my mesh loops. Killing this source creates a short circuit, so this is an enclosed area. There are no sources in this loop. This is an enclosed area. Killing this source opens this up. This is not an enclosed area. I can use a constraint equation to account for this loop. So I'm going to create this as mesh current I1, this as I2, and then I'm going to create a constrained loop that goes through this source and matches its magnitude and direction. It can go around here, it can go around here. I'm going to keep it simple and just confine it to this rightmost rectangle. Now I'm going to write KVL around each of my 2 mesh loops. I2 and I1, I'm expecting 2 equations and 2 unknowns. So loop 1, starting down here, I get a negative 40 volts plus 2 ohms times I1 is the only current going through that resistor, plus 10 ohms, which has both I1 in a positive direction and I2 in a negative direction. That brings me back to my starting point. It's 0. So 12I1 minus 10I2 is equal to 40. That's my first equation. Loop 2, starting at this point here, I have a 10 ohms. Now my I2 contribution is positive because this down here is assumed to be my positive node. So I2 minus I1 is going the opposite direction, plus 9 ohms times just I2, no other mesh currents go through the 9 ohm resistor, plus 4 ohms times I2, and this 1 amp constrained current is going in the same direction as I2, so it also induces a positive contribution. That sums to 0, so I end up with a 10, 19, 23 I2 minus 10 I1. This is a 4 times 1, which goes over to the other side. Those are my two equations and two unknowns. If I solve those, I get I1 is equal to 5 amps. I2 is equal to 2 amps. Keep in mind that those are not what we want. Okay, they don't correspond to anything that helps me really find out anything physical about this circuit. What we want is I10. It is positive I1 minus I2. I10 is I1 minus I2, which is 5 amps minus 2 amps, which is 3 amps. And it is actually positive downwards. This concludes my formal presentation of mesh analysis and nodal analysis. One thing you want to keep in your mind is that there's nothing new about these. They are simply rigorous methods of applying KVL, KCL, and Ohm's law in a way that makes your life easier. You're reducing the number of overall variables describing the circuit. You're making your analysis simpler. Now, just because I'm done formally presenting these doesn't mean that we won't see them again for the rest of the semester. We'll keep using all of our circuit analysis techniques, KVL, KCL, Ohm's law, circuit reduction, mesh analysis, and nodal analysis will keep showing up for the rest of the course. Okay? What we'll do is apply these tools in different ways and to different devices. For example, next time we'll start taking advantage of a systems analysis approach towards circuits. In Lecture 1, I said it's sometimes convenient to think of a physical device as being a system with some input and output. In Lecture 10, we'll start formally introducing and using that frame of mind.